Beyond Earth, uranium's role in humanity's next frontier. Space missions demand nuclear power in ways that Earth-based systems never encounter. NASA is actively researching small, compact reactors for space missions that could power Mars colonies and lunar bases. Space exploration creates completely new problems for nuclear power that don't exist on Earth. Engineers have to design systems that work in places where there's no air, no water, and temperatures that swing from boiling hot to freezing cold in minutes. Space presents unique challenges that make nuclear power incredibly difficult to use. Without air or water, space reactors must reject heat by radiation, which changes how they're engineered. The extreme radiation in space also damages electronic components much faster than on Earth. Most importantly, space missions need power systems that work perfectly for decades without any repairs or maintenance. Small modular reactors designed for space missions use uranium in completely different ways than regular power plants. These reactors are much smaller but need to be much more reliable. Engineers design them to run automatically without any human operators. The uranium fuel has to be processed to much higher standards because there's no way to fix problems once the mission launches. Even tiny impurities that wouldn't matter on Earth could cause major failures in space. Radioisotope thermoelectric generators represent another way uranium powers space exploration. These devices don't use nuclear chain reactions like regular reactors. Instead, they use the natural heat that comes from radioactive decay. The generators use plutonium-238, which is produced via reactor processing of uranium. This plutonium generates heat for decades as it slowly decays. Special materials convert that heat directly into electricity. The Voyager space probes show how well uranium-powered systems work in space. Both Voyager 1 and Voyager 2 launched over 45 years ago with plutonium-238 power sources. They're still sending signals back to Earth even though they've traveled billions of miles from the sun. Solar panels would have stopped working long ago at those distances, but the uranium-derived power keeps flowing. These probes will keep transmitting for several more years before their power finally runs out. Mars colonies and lunar bases will depend heavily on uranium power because solar energy won't be reliable enough. Mars gets much less sunlight than Earth, and dust storms can block solar panels for months. The Moon has 2-week-long nights where solar power stops completely. Nuclear reactors powered by uranium can generate electricity constantly, regardless of weather or sunlight conditions. This reliable power will be essential for life support systems, manufacturing equipment, and scientific research. Uranium also enables advanced space propulsion systems like ion drives. These engines create thrust by shooting charged particles at extremely high speeds. Ion drives are much more efficient than chemical rockets for long-distance travel, but they need steady electrical power for months or years. Only nuclear power systems can provide that much energy reliably for extended space missions. Chemical fuel would be too heavy, and solar panels become useless in the outer solar system. Space-grade uranium processing requires even higher purity standards than the most advanced Earth-based reactors. Every atom in the fuel has to be perfect because there's no way to service or replace components during space missions. The enrichment process has to remove even more impurities than normal. Quality control testing is far more extensive. Engineers test every batch of space fuel much more thoroughly than fuel for Earth-based power plants. If uranium-based systems can last decades in deep space, what does that mean for Earth-based power? Uranium-powered systems will provide the reliable baseload power that Mars colonies need to manufacture everything from building materials to life support equipment. These same systems will enable spacecraft to travel beyond the solar system by powering ion drives and keeping life support systems running for decades. The manufacturing capabilities that uranium power provides will let humans build sustainable settlements that can grow and expand without depending on supply missions from Earth. From spinning centrifuges to space exploration, uranium has transformed from an almost worthless element into the foundation of humanity's most ambitious energy projects. In conclusion, the technical breakthrough that made this possible changed everything about nuclear energy. Uranium's journey from a nearly useless rock to humanity's most energy-dense fuel represents one of science's greatest problem-solving achievements. Scientists took an element that was 99.3% worthless and figured out how to extract the tiny fraction that could power entire cities. The trick was enrichment, concentrating the 0.7% uranium-235 up to 3% to 5% for reactors, which is what made nuclear power practical. The same thinking that solved uranium's separation challenge can help tackle other seemingly impossible energy problems today. When something looks too difficult to solve, remember how scientists turned uranium's biggest weakness into its greatest strength. This element may play a major role in powering both Earth's clean energy future and humanity's expansion into space. If you enjoyed this breakdown of how spinning machines solved nuclear power's biggest problem, hit that like button.